So in this video and the next one we're going to explore a rather interesting construction where we can use some number theory to create a particular kind of a block design called a quadratic residue block design. So it's based on this theory of quadratic residues, so that's what we're going to explain in this video. So we have to start, let P be a prime of the form 4n plus 3. Okay, so for example 3, 7, 11 are all primes of the form 4n plus 3. The next prime 13 is not of the form 4n plus 3. And about half primes are of the form 4n plus 3. Okay. So then we're going to consider the field Z mod P. Okay, so yes, most often you kind of think of the elements of this as being the numbers from 0 up to p minus 1, which is 4n plus 2 at the moment, in this case. But it's actually better to kind of think of this in a more symmetrical way, as kind of 0 and then plus or minus 1, plus or minus 2, plus or minus 3, all the way up to plus or minus 2n plus 1. So for example, we could do Z mod 7. That's 0, 1, 2, 3, 4, 5, 6. But if we're working mod 7, then your 4 is the same as minus 3, 5 is minus 2, 6 is minus 1. So this is the same as 0 plus or minus 1, plus or minus 2, plus or minus 3. Okay, so then we're going to define Q is a set of quadratic residues. That's what they're normally called. That's just a set of all things that are squares. Okay, so let's do the case P is 7. Well, if you take plus or minus 1, I would say, yes, I should have said here we're not considering 0. Okay, so let's just adjust that. Yeah, so this is a non-zero squares in Z mod P is what we're calling Q. Okay, so in Z mod 7 we have plus or minus 1 squared, that's always equal to 1, and plus or minus 2 squared, well that's 4, but working mod 7, so 4 is the same as minus 3, and plus or minus 3 squared is 9, which again working mod 7 is the same as 2. So our Q, you've got 1 and then 2 and then minus 3. So that's what happens in Z mod 7. Let's do the same exercise mod 11. Okay, in Z mod 11, well we get there with Z mod 11 is kind of, you've got the numbers plus minus 1 up to plus minus 5. Plus minus 1 squared is 1 again. Plus or minus 2 squared is 4. Plus or minus 3 squared is 9, which is minus 2 mod 11. Plus or minus 4 squared is 16, which is 5 mod 11. And plus or minus 5 squared is 25, which is 3 mod 11. So we see that quadratic residues in this case, you've got 1 there, and then we had minus 2 there, and then 3 there, and then 4, and then 5. Okay, so a pattern that we notice here is in both of these cases, you've got just in your Q you've got the numbers 1, 2, and 3, except that some signs are plus and some are minus. And in this case, again, you've got your Q is 1, 2, 3, 4, 5, except that some of them have an attached minus sign. And so that's a kind of general thing, and which we'll explain in a minute. Okay, so the kind of generalization of what we just observed a second ago is this proposition here. if P is 4n plus 3 is prime, then for K is 1 up to 2n plus 1, precisely 1 of K and minus K lies in Q. And as a consequence of that, you see that the size of the set Q is going to be equal to 2n plus 1. Okay, so the proof will so the set U, we'll call this U, is Z mod P with 0 removed. So that's all these things here. So this is a group. Under multiplication mod P. Okay, so that's not 100% obvious. It's not 100% obvious that everything has an inverse, but that's true just because of the fact that P is prime. I'm going to assume that you remember that from the algebra course. Okay, so so we're going to define alpha from U to U by alpha of U is U squared. Okay, everything being interpreted mod P as usual. So this is a homomorphism. And what's the image of it? Well, the image is precisely the set of squares, which is Q. So the first isomorphism theorem says that the size of the image is the size of the full group divided by the size of the kernel. That's at least a consequence of what the first isomorphism theorem tells us. And so what is the kernel? So this is the set of things U for which U squared equals 1, which is the set of U in Z mod P, where U minus 1 times U plus 1 equals 0, right? Because U minus 1, U plus 1 is U squared minus 1, and so U squared equals 1 is equivalent to this thing here. So because we've got a field, every non-zero thing's invertible. We see that this is just the set 1 comma minus 1. So the size of the kernel of alpha is 2, and the size of the image of alpha. So therefore, from that we conclude that mod Q is mod U over 2. But the set U had size 4n plus 2, so this is size of Q is 2n plus 1. Okay, so yeah, it was at least a consequence of what we're claiming, that the size of Q should be 2n plus 1. So we're not quite, so we've still got a couple more steps, but that's a good way forward. So now I know, so the next claim is going to be minus 1 is not in Q. Okay, so so how can we see that? Well, if minus 1 was a square, then well, in particular that means that U squared is not equal to 1, but U to the 4th equals 1, therefore U has order 4 in our group U. But remember that the size of U was 4n plus 2. So that's not divisible by 4. And Lagrange says order of any element divides the order of the group. So that means that no such U can exist. Okay. Okay. So now we see that Q subgroup of U, and we've seen that the size of Q is 2n plus 1, which is half the size of U. Therefore, there are precisely 2 cosets of Q in U. Also, minus 1 is not in Q, therefore minus Q is one coset, and Q itself is the other. So therefore U has got to be a Q disjoint union with minus Q. So that means that if you've got to look at K is 1 up to 2n plus 1, precisely 1 of K and minus K lies in Q. Okay, so that was the proposition we were supposed to be proving, that for each of these numbers, 1 up to 2n plus 1, if you look at K and minus K, one of them is in Q and the other one isn't. And we saw how that worked out in the case P is 7 and P is 11. It was easy to just calculate which ones are squares and which aren't. Okay, so there's one more numerical fact about quadratic residues that we're going to need to feed into our construction of a block design. So that goes like this. We're just going to put D as the set of pairs U, V in Q cross Q, for which U and V are different. So this set we can count easily enough. So we get we just choose one element. I'll choose element of U in Q. The size of the number of choices for that's just the size of Q, and then once we've done that, well, V has to be. Also, I said U and V are different, right? So V has to be different from U, so you get mod Q minus 1 choices there. But we worked out that the size of Q was 2n plus 1. Remember here, P was 4n plus 3, and the size of Q we showed on the previous screen was 2n plus 1. And then that's times 2n, and it'll be convenient to just rewrite this slightly. This is 4n plus 2 times n. Right, and then we want to split up this set D into some subsets called dx. Okay, so this is just the set of pairs UV in D, where U minus V is equal to X. Okay, so this set dx is a subset of D. So of course, you look at this D. I mean, each of these, any U, V, and D. I mean, U and V are different. So U minus V is going to be some non-zero element of Z mod P. So this pair uv lies in one of these sets dx, and of course these are disjoint. So that means that the size of d is the sum for x not equal to 0 of the size of dx. And so the claim, this lemma, is that in fact the size of dx is going to be equal to n for all x. Okay, so so in fact, so how are we going to prove this? Well, it's actually going to be enough to show that all the sets dx have the same size, right? If they all have the same size, then in this sum here, well, how many terms have you got? This is taking the sum over x not equal to 0 in z mod p, so you get p minus 1 choices for x, but p was 4n plus 3, so p minus 1 is 4n plus 2. So you just, in this sum, you just get 4n plus 2 terms all the same, and the total has got to be equal to the size of d, which is 4n plus 2 times n, so that means each term's got to be equal to n. Okay, so we want to just, in order to prove this, we need to show that all the sets dx have the same size. Okay, so let's just write that again. So dx, that's the set of pairs u, v in q cross q, with u minus v equal to x. And here we're assuming x is some non-zero element of z mod p. And so we want to claim that the size of dx is the same. Well, we want to claim that they're all the same size, so in particular it's going to be the same as the size of d1. And so there's two cases. Okay, so we proved a few minutes ago that if you look at any non-zero element of z mod p, then it could be a square. Either it's a square or minus it is a square. One or the other happens. Okay, so we've got two different cases according to whether x is a square or minus x is a square. Okay. So in case A, well, we can define f from d1 to dx by f of uv is just ux comma vx. Okay, so now what's going on here? I mean, this is valid because in this case x is a square and u is a square, so u times x, that's also a square, right? It's clear that the product of two squares is a square. So here, the pair uv was in this set dx, which means that u and v are both in q, they're both squares. We're multiplying by x, which is in this case we're also assuming is a square, so ux is a square, vx is a square. The pair uv was supposed to be in d1, so u minus v is 1, so we multiply by x, ux minus vx is equal to x. So that means that this pair ux comma vx does indeed lie in dx. And this is bijective with, obviously f inverse of u prime v prime is just u prime over x, v prime over x. Okay, so here we're kind of using the fact that z mod p is a field, so division works perfectly well mod p. Or division by non-zero things works perfectly well mod p, and we're assuming here that x was non-zero. Okay, so this is a bijection, and so that proves that the size of d1 is equal to the size of dx. And case B, so again, we're going to define a bijection from d1 to dx. We just have to use a slightly different formula. Okay, so this one's valid because in this case we're in case B, so minus x is a square and v was a square, so you multiply minus x by v, that's a product of two squares, so that's a square. Similarly here you multiply minus x by u, that's a product of two squares, that's a square. So both of these guys are squares, and if you take this one minus this one, then that's going to be the same thing as u minus v times x, which is here u comma v was supposed to be an element of d1, so u minus v is 1, and so that follows that minus vx minus ux, that's the same thing as u minus v times x, which is equal to x, because u minus v is equal to 1. Okay, so again this is so that's bijective with, again, f inverse of u prime v prime is minus v prime over x minus u prime over x. Okay, so because we've got a bijection like that, again we see that the size of d1 is the size of dx. Okay, so that proves this kind of subsidiary claim that the size of dx is equal to the size of d1 for all x. But we really wanted to prove that the size of dx is actually equal to n, so we'll do that in just a second. Okay, so now let's recall we had that the size of d was the size of q times size of q minus 1, which is 2n plus 1 times 2n, which is 4n plus 2 times n. But also d is a disjoint union of the sets dx. So we see that the size of d is the sum over all these x's, and remember that these x's were in the set z mod p with 0 removed. Okay, and so we look at this this sum here. What do we got? So we've got p minus 1 terms, and p minus 1, which is the same as 4n plus 2 terms. And each of those terms, we proved that there's, the size of dx is always exactly the same as the size of d1. Okay, so we've got 4n plus 2 terms, each of equal to size of d1. So this is equal to 4n plus 2 times the size of d1. Okay, so but we know that the size of d, we already said, is 4n plus 2. So just putting this together, we've got 4n plus 2. N is 4n plus 2 times the size of d1. So the size of d1 is n, and so the size of dx is equal to n for all x, because we proved just a minute ago that all the sets dx have the same size as d1. We had bijection from d. We had a bijection from d1 to dx for all x, so these guys are all the same. So this was the key claim that we wanted to prove, and in the next video we'll show how to use this this fact to produce an interesting block design.